This is MatLab Line Fitting, and we need to go over some properties of logs before we go on. So, as a reminder, if you have x equals 20, the natural log of 20 is 2.99, and e to the 2.99 is 20. So that's how you go back and forth. Likewise, with log base 10, so if x is equal 20, the log base 10 of 20 is 1.3, 10 to the 1.3 gets you back to 20. And this is standard nomenclature. This is typically how you write it. That's log base 10, and that's natural log, typically. But in MATLAB, it isn't that way. So it gets confusing, and you just need to remember that the natural log in MATLAB is written log, and the log base 10 in MATLAB is written log10. Just need to remember. All right, going back to our files, we saw this earlier, the plotting, and here we go. Let's look at this data that's rectilinear. So what I did was to demonstrate, I took a function d equals 2t plus 8 just as an example, and I put down numbers that are close. T is that, and then these d's, you can tell very quickly, they're pretty close to this function but not quite. So they represent measured data. All right, so what we're going to do with this is we're going to go in and we're going to plot it. And I think all this makes sense. I think you know everything here. All right, so let's plot it and see what it looks like. And there it is, and it's what we'd expect. It's all labeled. Now, what we're going to do is we're going to create the line of best fit. So, let's first look at what happens here. This hold on, we're going to plot this data, and we're going to plot the line of best fit. So the hold on command allows you to plot multiple data on top of each other in a single figure. So if we run this, nothing different happens. It's just ready to get more. All right. To get the coefficient of best fit, the coefficients of best fit. So here this is my name, uppercase C, uppercase E. So this is going to be where the coefficients are. Then there's a magic word in MATLAB, polyfit, and it takes as its arguments the x values, the y values, and then 1 means it's a linear function. So the coefficients for this data, the coefficients of the line of best fit. So let's run it, and I run it. So if you look at the workspace, D and T are what we'd expect, and now here we have two coefficients, it's a 2-element vector. The first element is 2.01, the second element is 7.95. What these are the first element, the first element is M, the second element is K. So if we want to isolate M, we do it this way, we run, and you can see that we pulled M out of the coefficient vector. So now we have just M there. That's good. Now we'll pull K out. There's K. So that's good. And now what we do is we now find the y's of the line of best fit. So we have the original t's, and we're going to calculate the y's, and we use y equals mx plus b is the way you're used to seeing it, but this should look familiar. So we go ahead and we run it, and now we've got the best Oops, didn't. And now we have the y's of the best fit line, and we can plot those. And there it is. I should say on the plot we used as a point indicator an R. That means no points but a red line, and you can see how it fits. So that's linear. Now if we go to, let's go to power next, and let's comment all this out. So what we're going to do is, here we have new data, and this is radius of a circle, and these are the measured areas. So they're going to be, I made them a little bit off so you could see a difference, but we know what the relationship is. But let's see if we can pull that relationship out of here. All right, so I'm going to uncomment all these. I don't think anything's new. We talked about the axis. It's common to do the axis on logarithmic paper because you want it to start and end on 1 times 10 to the something typically. Okay, I think that all makes sense. So let's run it. There it is. There's the log paper. 1 cycle in the X, 2 cycles in the Y. All right. Now, these two are the same as before. The coefficients. So we use the same polyfit command or built-in function that we used just with the linear. Same thing. But now we use the linearized form of the equation. And so that means we take the logs. So remember, this equation should look familiar. That's the linearizing the power function. So we need to take the log base 10 of the x's, the log base 10 of the y's, and then it's a linear equation. So let's run that. Oh, sorry. Let's run that. And here are our coefficients. Our coefficients are 1.99 and 0.5. Now, we'll pull out the m coefficient and run it. And we can see that m is 1.99. We know it should be 2, so that's very close. So we isolated it. And we don't, that gives us m directly. But now we're going to calculate k. So this is the confusing part. We run and we pull out the k. But unlike the m, here's what k is originally. But it turns out that that's the log base 10 of k. And you can see it because here it is. It's the log base 10 that we're working with. The m, for example, it was the m. There was no logs taken. But here we end up with the log of k. Because we end up with the log of k, in order to get k itself, is we have to raise it 10 to the log k. And notice here, we raised it, we used the dot caret. And again, I think I mentioned this earlier, you want to get in the habit of using dot caret, dot divide, dot multiply. And it's an issue with the way MATLAB works with vectors. So that's how we get k. So k comes out of 3.16, and we know it should be 3.14, so that's close. And now the line of best fit. We calculate the y's of the line of best fit. Then we go back and we have, that's the equation, that's the standard form of the equation, and so we bring it back to the standard form of the equation here. So we get the values of the line of best fit, So here they are. And they have the same number of elements as the original data did. And then we plot it same way as we did before. And there it is. Okay. Last one we'll do is exponential. So here's the data again. And we're going to go through and we're going to, let me comment all this out. So we're going to go through and we're going to first plot it. Semi-log y is a magic word. Its arguments are the x values, the y values, and the point styles. So that makes sense. Comment x label, y label, title, same thing. Grid. So let's run this and make sure that all works. So yes, we have a linear grid and a log, 2-cycle log y. So that's right what we want. Points are pretty straight. So now let's go in and these two lines, this line you're okay with, I think. This line. So now we're going to pull the coefficients again. Again, that is that's my labeling. That's not a magic word. That's just what I call it. This is the magic word. And it has 3 arguments again, and it's the x values, the y values, and the type of function. In this case, it's linear. And if you recall, in the linearized form of this function, we took the ln's, we took the natural logs of the y's, but we did not take the logs of the x's, and that's because of the axes. You can think of it that way. So we're doing a polyfit of the plain old x's against the natural log of r of the y's. Remember, this log means natural log. Confusing, I know. So that's what we're going to do. So if we run it, here is the vector for our coefficients. So it's 0.07 and then 8.6. Now we pull out the m value just like we did before. And there it is. We pull it out. And now the k, because we have the ln of k, we have the ln of k because of this. The m itself is fine, but the k, we have the natural log of it. So to turn the natural log of something into the number, you take it to the e. So exp is e in MATLAB, and we run that. And now we've got the k, and this is the same as, well, it's not the same. Now we go ahead and we calculate the y's on the line of best fit, and we put it back into its standard form. So it's k times e, again notice the dot thingy, k times e raised to the m dot l. And now we'll plot it. And there it is. Thank you.